Hello, it's the hopefully last podcast on guidance and control. I'm sort of a little, I guess I'm more self-indulgent on these topics when I'm doing it as a podcast because I always figure, well, I don't need to rush. I can always do one more podcast if I don't finish it, and it allows me to go off in a bunch of tangents, which, as I've said several times, I feel a little guilty about doing that. On the other hand, students often tell me that it's the most interesting part of the course. So, and there's kind of a reason for that, which is that basically, if we want to know about, how spinning satellites are used for guidance and control in space, there's a lot of books you can read about that. But the case, kind of the case studies and what goes right and what goes wrong, and how things are really done in practice, and just a totally biased individual person's point of view, as I kind of gave you about gravity gradient. Because, I'm sure you'll find people in the world who totally love gravity gradient, and, it's not that I hate it or love it, but I think I'm just a little less naive about how wonderful it is. And I'm the same way about magnetic, to tell you the truth. I've done, several, AMSAT did a lot of magnetic satellites. It depends what you're trying to do. But, what we were trying to do was point an antenna more or less parallel to the surface of the Earth when we were going over North America. And it worked pretty well for that. So, everyone has its applications. I think that the problems come in when you try to do more with the passive than it's really capable of doing, and you end up making it, what they call enhanced. And enhanced is really not passive, because how do you enhance it? With active control, and then you pretty much have taken on the worst of both worlds, in that you're having to build an entire active system, and yet you're trying to work within the envelope in which sometimes very weak torques are going to be controlling. That it sounds like a kind of a meandering conversation, but that really brings me to spin stabilization. And I have to say, maybe you can tell from the undercurrent of this course that I was not like a fantastic student, and I had a lot of trouble with, various topics that I looked around myself and the other students weren't having as much trouble with. And sometimes it turned out that was actually true. I mean, all the various states of the diagram were in there. Sometimes it turned out I really wasn't getting it as well as other people were getting it. Sometimes it turned out that, nobody else was getting it either. And I had a very interesting experience in a course at Stanford that was taught by this super genius guidance and control guy. And he was so far over my head. I mean, I just went to class and just figured I'll try to understand anything of what he's saying. And I tried to take notes, and I couldn't really even take notes because I couldn't tell what he was getting at. And everyone else in the class looked so serious, and I'd never had a dynamics class at Brown, like 137. This was my very first class, and I just thought, okay, I know nothing about this. And, what could you do? I just plowed through the course. It was part of the required core, and I was brand new at Stanford, and I just figured, well, I'll do the best I can. I'll read the chapters when he remembered to even make an assignment. And I ended up getting a 30-something on the final exam, and it turned out to be one of the higher grades in the class. So, I'm looking around at all my classmates, who looked so serious and looked like they were really getting it. Nobody was getting it. I mean, we were all in the 20 to 35 range, I think, on the final exam grade, final exam grading. So, I've had that experience. And then I've had occasionally the experience where I really was getting it. And that's probably why I went into thermodynamics, because I always got it. It just made sense to me. So spinning and in general dynamics gave me a lot of problems, and I think that's why I decided to do automatic control for my master's degree. I felt like, okay, this is the thing I'm the worst at. And, what the hell difference does it make? At least I'll, won't be the worst at it anymore if I spend a year or two of my life. And it interested me. It's a super interesting topic. How you do it. If there was one thing about space that I wondered about, it was, how do we point these things? And how do we know where they are? And I still wonder about that. There's a professor at my university here who has worked many years with JPL. He's an Italian guy, and he visits there every year and so on. And he's a deep space navigator. He figures out where objects are. When you think about it, we kind of take that for granted. And of course, we normally call this guidance, navigation, and control, and I don't really do the navigation part at all. We do a little bit on orbits. And it's really fascinating how they work, to use larger and larger baselines, like the Earth-Sun baseline and things like that, to triangulate the position of these very distant objects, and the time of flight. And when you really think about it, it's a pretty subtle art to navigate a spacecraft. We take it for granted that we can just send things and they land on Mars. But, go out on the roof of your, condominium like I do in the summertime and go find Mars in the sky. It's not that easy to even find it, unless it's super bright like it was last summer. So right now I'm focusing on the guidance and control and not the navigation. But when we talk about orbits, I do talk about it a little bit. Well, spinning, why do we even care about it? I mean, maybe that seems like kind of an obvious question, but it all has to do with integration. If you have an object in torque-free motion, just no forces acting on it, torque-free motion is already a pretty abstract idea that took me a long time to get my head wrapped around. What exactly, is torque-free motion and how do things behave when they're in torque? It's sort of obvious, right? I mean, if it's not moving, it continues to be not moving in terms of its attitude. But anyway, when you apply an impulse, which would be, a Newton meter second, a certain torque for a certain period of time. So when you apply an impulse to an object that's not spinning, its angle, let's say even if you're only working in, the two-dimensional plane, it starts turning, like a LP record on a record player. And, if you don't if that's such a random torque, right? It's, you got hit by a tiny piece of dust or, a little bit of solar wind as you were coming around part of the orbit, or, you turned something on and it made a momentary electromagnetic field and that reacted with the Earth and gave you a small disturbance torque. We've used that word a lot. You don't know anything about that. It's a random thing that came out of the blue sky, so to speak, or the black sky, as the case may be. And it started you moving. And you have really, if you let a certain amount of time go by, you have no idea anymore what your attitude is. That's the nature of a non-spinning object. If you give it a torque impulse, it starts rotating. And, since you don't know the nature of that torque impulse, you don't know what axis it's rotating on or how fast. So you very rapidly lose track of what its attitude is. What's the magic about a gyroscope? The magic about a gyroscope is it's kind of an integrator. Instead of just going in a constantly evolving time history of angle displacement, the reaction to a torque impulse, a Newton meter second, is a finite change in the attitude. So if you think about that with a gyroscope, if you push it with your finger, it doesn't, depends, on your gyroscope, but in general, you will change the spin axis by a fixed amount. It won't just keep rotating around and rotating around. No, it stands on the table. It may be gyrating about its vertical axis, but always with a constant angle. So that constant angle is proportional to the torque, what I call the torque impulse that you apply to it. So in a sense, it has like a memory of where it was. Any torque impulse doesn't just generate a constantly evolving angle that gets bigger and bigger and bigger compared to the start point until it comes all the way around, let's say 360 degrees. If it even does that, because in 3 dimensions, as you know, if you're moving on different axes, it may never come back to the same state again. Instead, with the gyroscope, every torque moves it a finite amount and just changes the spin axis by a finite amount, by a degree or 5 degrees. What's really cool about that is your disturbance torques are normally random. And if your angle displacement is small, that the root mean square, let's say, of all those random torques will integrate out to 0. And so it's very, very stable in the face of random disturbances. And Whereas if you have something and you flip it 180 degrees on one axis, and it turns 90 degrees on the other axis, as many of you probably well know even from statics or dynamics, and then you give it the opposite kick, it's not in the same orientation anymore. It's not going to go back to where it was before. Whereas a spinning satellite will, and just in layman's terms, it's stiff. The attitude is really stiff. And that means if you point it in one direction, it's going to keep pointing in that direction. So that can be, highly advantageous if you want to, point at the moon. If you want to, I worked on a spinning satellite, a super interesting spinning satellite that wanted to point at stars one at a time. It was measuring the variation in the light output of stars. It was called MOST. Micro oscillations in the brightness of stars. I don't remember exactly how the acronym worked. So the idea was to keep the camera exactly pointed, always the same pixels on the star, because the pixel-to-pixel variation in sensitivity would swamp the actual changes in the star brightness. And that was, done that way by spinning. So it, for an inertial target, it will spin, will do really well. We used to build radio reconnaissance satellites with big directional antennas. I don't know how they do it now, this is a long time ago. And we only wanted to, spy on one particular point on the surface of the Earth. So we would spin it so that when the orbit went over that point, the antenna was pointing exactly there. Then when we changed target, we would move the spin axis around, and then it would, every orbit, point at that same target again. So the spinning is very useful, even though part of the reason I went into that monologue about my difficulties in dynamics is that spinning is really complicated. From a mathematical analysis point of view, I found it very difficult, and I fought against it. I didn't want to admit that spinning, was useful, and like spin stabilized satellites are pretty rare, you might say. And I kind of convinced myself, well, this is kind of a special case that I don't really need to know about, but I mean, I guess we all play these mental games with ourselves when we're in class and try to convince ourselves that, the one thing we don't want to study or that we don't like isn't really that important anyway. And I was doing that. Okay, so you can take a satellite like the one that's shown, on slide number 23 and on the right, the original the first geosynchronous ComSat that was built by Hughes. And it's a very interesting satellite because with the propulsion system, with blah, 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 I mean, you look how small it was. And, it had 50% of its mass in a kick motor to get it to geosynchronous. And, but it worked. And nowadays, if you proposed a 37 kilogram geosynchronous satellite, people would really give you a hard time about whether it would work or not. And you had to say to them, gee, guy, 60 years ago, it flew and it, relayed television and radio signals from geo. So that was, basically a very simple spinning satellite. We graduated up from just spinning a cylinder, which is really not a bad idea. And the very first satellite my company built was that. It was just a spinning body, a rigid body spinning. So the whole body, the cameras, the antennas, everything was spinning. The next step up from that was what they called the dual spinning, which is a little bit confusing. I mean, it is, theoretically speaking, dual spinning. What you would say is that it's partly spinning and partly not spinning, as in the little diagram that I drew there. So you basically have some sort of a bearing that attaches the two parts of the satellite together with commutators, because usually the solar panels are on the spinning part, and you have to get the power up to the not spinning part, and so you've got to have some sort of a sliding contact, which is really amazing that it actually works. But anyway, the idea is that you have the advantages of a spinning satellite, but you have a despun platform that isn't spinning, that you could put, let's say, a telescope on that despun platform, and it wouldn't be spinning around. It's okay if you want to measure the brightness of a star. The pixel can be rotating around the target. But if you want to take pictures of the moon, you really want to be pointing at the moon. There are people who've said, well, if the object's really bright, like the moon, I don't care if I'm spinning slowly, I'm going to take a short exposure and it won't blur relative to my pixel. That doesn't convince very many people much of the time, that idea. So you know, there are very few. Hughes got a patent on the dual spin satellite. I mean, they call it dual spin because, in a certain sense, it depends on your point of view. It's just the two things are spinning, let's say, with different angular rates. So if we put ourselves in one frame of reference, there's part of it that's stationary if we view it, from that point of view. But you could also say that the two parts are spinning relative to each other at two different spin rates, whatever. Hughes got a patent on that, and for 17 years milked it like crazy, the length of the patent's life, because it was the predominant way to build geosynchronous satellites. And it built Hughes into the gigantic company that it became, that single idea. But if you take that idea a little bit farther, make the not spinning part super big, and make the spinning section super small, what you have is a modern, what we call a three-axis stabilized satellite. What everybody thinks, is a satellite. You watch the Hubble. Hubble is a three-axis stabilized satellite. It has a spinning component and a not spinning component. Most of the satellite is not spinning, and then it has little wheels. Maybe not so little, but it has wheels that are little compared to the size of the whole Hubble, and they are spinning. So in a sense, it's more than a dual spin satellite. It's probably a quadruple spin satellite. It probably has 4 momentum wheels spinning along the 4 principal axes normal to the faces of a tetrahedron. So we'll get into that in a minute, why you would do that. And I can see already we're not going to get through this whole thing on spinning satellites in one podcast, but whatever. So in a way, three-axis stabilized satellites are quote-unquote dual spin satellites. The idea of many, probably the predominant form of stabilization of satellites is to have a non-moving stationary platform stiffened by having spinning wheels. And usually you'll see, intuitively you would say 3 wheels, X, Y, and Z. The trouble with the 3 wheels is that if one of them fails, you've totally lost that axis. So, I have a slide on this that we'll get to, but typically they have 4 wheels. The interesting thing about the Hughes dual spin was it basically had 1 wheel. And later on, much later on, it was 1990 something, so we're talking 30 years later on after Hughes, we proposed a 1-wheel satellite, and people, didn't accept it. And that's part of the story of small satellites in general. Is I used to tell people, we didn't invent anything. We just, modernized ideas that had already been come up with in the late 50s and early 60s when we didn't know how to build big satellites, and the only satellites were small satellites. And really, this was the beginning of the idea, SYNCOM, was the beginning of the idea that satellites would use angular momentum to stabilize themselves. Okay, so the story on spinning that I just recounted verbally is sort of on slide number 24. A non-spinning body subject to a torque impulse, and I sort of characterize that with a little finger pushing on an edge of the satellite, will begin to tumble, and it'll just keep doing that. It'll just keep going round and round and round. And you'll have totally lost what your attitude was before that random torque, touched your satellite. On the other hand, a spinning satellite, if you apply a torque to it, you'll displace the spin axis, by a fixed amount. So, and depending how fast you're spinning, that fixed amount can be extremely small. We launched a satellite that was spinning at, there were 2 versions of it, 2 designs of it, but the ultimate one, when it was flying, it was spinning at half an RPM. That's not super fast. You look at the second hand of a watch, it was going half that fast. But the disturbance torques were small enough that spinning half an RPM, we were able to maintain its attitude to better than 1/10 of a degree. And that's because the disturbance torques are really small. And the satellite was fairly heavy. It was over 100 kilograms. And, you have a body that heavy. If you think about a 100 kilogram, wheel spinning around, it's fairly rigid. And that's the way the satellite, was. So actually, that's a little bit of a diagram on this page of what that satellite looked like. And it was partly made stable for spinning by the 4 solar panels that were deployed, from the base. And they all had objects on there. We had put some of the instruments on the solar panels to make them slightly heavier so that would be the maximum moment of inertia axis was the perpendicular to that axis, so it'll be a stable spinner. That satellite, to give you an example of how we use the spin satellite, those solar panels were stabilized to point at the sun. So that maximized the amount of power because the solar panels were always pointing directly at the sun. And that's an inertial reference more or less from the Earth. I mean, every day you develop 1 degree of error. Over the course of 6 months, you have to be pointing in 180 degrees different. So you actually have to move the spin axis 1 degree a day, which we did with magnetic torque coils, just using the H cross B. That's not a lot of moving the spin axis, but it adds up over time. But you can navigate completely with a sun sensor. All you need to do is maintain the sun. You don't have to know what you're doing. You just have a feedback controller that says, do I have an error relative to the sun? It's like, yes, okay, well, push on it. It's easier to do it if you don't need to maintain a certain angle. You're just trying to zero the error between the spin axis and the axis to the sun. So it was a little bit, in a way, we didn't think about it as hard as you could think about it if you wanted to do that, some other way. Like saying, okay, it's October 2nd, what's the angle to the sun? That would be a lot harder problem. We just had a simple feedback controller that said, point this thing at the sun as best you can all the time and spin at half an RPM. Okay, this next one is, it's kind of lost in history. I think I learned about it in the 70s or 80s, and the term is not used anymore. I've been all over the internet trying to find out where the name Thomson spinner came from. And I've even asked a couple of other, professionals, book writers in the field. Nobody remembers even if it ever existed. It's an interesting satellite because if I go back to 24, I said that the maximum moment of inertia tensor was, on the spin axis. The axis that goes, you can see the arrow going through the satellite with the arrow turning around it. If you have a maximum moment of inertia tensor, that's going to be the way that the satellite wants to fall into the gravity gradient, meaning that it really wants to spin like in slide 25, the green one, Thomson non-spinner. It really wants to spin so that the spin axis, it's an obtuse way to say it, but is perpendicular to the plane of the orbit. I don't know how else to say it. The spin axis, the other way I say it is the satellite is rolling on the surface of the Earth, the way a penny would roll on, a big spherical object. That is the way the spin, and that was our biggest disturbance torque on that satellite that was spinning. It was around 400 nautical miles in altitude. And so, you're talking 600-700 kilometers, fairly high up, but right in the prime gravity gradient, zone where gravity gradient is still fairly strong and atmosphere fairly nil. And what it wanted to do all the time was turn its spin axis so that the spin axis was perpendicular to the orbit plane, and that was our principal disturbance torque. So one thought of someone a long time ago was, all right, let's go with that. Let's spin the satellite so that the spin axis is perpendicular to the orbit plane. And that, at least a million years ago, was called a Thomson spinner, or at least that was what it was called in some crazy article that I must have read, and it impressed me. And in fact, it never made it into the textbooks, that nomenclature. But people know what you're talking about when you say that the spin axis is perpendicular to the orbit plane. Or you can say, okay, so it's in the orbit, normal. And the advantage of that is that the gravity gradient stabilizes your spin axis. So it's almost a passive, take an object, put a wheel in it, spin the wheel up, and leave it alone. And eventually the wheel will be spinning. And if you think about it, if there is gravity gradient torque and you spin the wheel on any other axis, it's going to constantly have disturbance torques, which are eventually going to cause it to be in that. How useful is that? Well, it could be very useful because you could do a dual spin, meaning one momentum wheel, one spinning wheel, and that's what I show on this diagram on slide 25. Put a wheel in there, spin it up, and de-spin the body. Now you have a cylinder, a square, a cylinder, or whatever, that's not spinning, that has straight down on one of its faces. If you have a motor or if you have torque coils that you can cause that thing to despin the rest of the satellite, okay? Because when you first spin up the momentum wheel, the rest of the satellite's going to spin in the opposite direction, but you can get rid of that angular momentum with torque coils, let's say, or with propulsion if you wanted to. At that point, the satellite can be steered to point straight down. And that ability to point straight down could be used for taking pictures off the side of the satellite, as it's shown in that kind of grainy illustration. These illustrations were pulled from the illustrations in my 1995 book. So, the quality of graphics back then was not that good, but they tell the story okay. The other thing that it does is you could put antennas, little stick antennas, along that spin axis. Little stick antennas, just a regular piece of wire, straight piece of wire, radiate off of their sides. They radiate perpendicular to the axis of that straight thing. So if you think about a car antenna, the old car antennas that were vertical on the car, the radiation angle is exactly horizontal. When you look up and you see, like, police stations have radio antennas, the antennas point straight up. They're not trying to communicate straight up. They're trying to communicate horizontally to reach police cars that are basically horizontal to them. And they're up in the air so that they extend their horizon a little bit so that they can see a little bit farther, get over the clutter of the local trees and buildings and stuff like that. But basically, they're radiating horizontally. Dipole antennas, that's what they call them. These stick antennas, like car antennas and like those VHF antennas, it's, people, radio amateurs use them, citizens band people use them. All kinds of devices have these little stick antennas that are just a simple pole sticking up in the air, radiate off of their sides. And so that gives you a very strong signal down to Earth. It also gives you a very strong signal away from Earth. So how strong is it? It's about twice as strong as it would be with a random isotropic orientation. It's 3 dB for free, let's say. So there's a couple of little advantages to it, not enough advantages that very many people do it, because if you have the magnetic torquers to play around with the body and despin it relative to the wheel, then you could really point it in any direction you wanted to and just use the torquers to overcome the little bit of gravity gradient torque that's going to disturb you. So, okay, the next slide, it's another green one that says Sun non-spinner. This was the second generation of satellite that my company built. The first one was actually spinning on the, this diagram was actually the very first one. That's the model of it is shown in the Los Alamos Museum there. It was spinning, pointing at the sun. In order to make it into a non-spinner, we put a momentum wheel on the satellite, and that way the wheel had the angular momentum stored up in it that made the gyroscopic effect of stabilizing the satellite. And it doesn't really stabilize the satellite, it stiffens the satellite. Stabilizing implies that you have some sort of feedback control loop and you manage to sense an error and correct for it. When you just put a wheel on something, or you spin in the body, you're not stabilizing it in an active sense anyway, you're stiffening it. I mean, when you spin a bicycle wheel like you're riding a bicycle, that gives you stiffness. But if you don't hold on to the handlebars or be very careful about your weight so that you can, ride it no-handed, it's still going to crash because it's not stabilized, it's rigidized by the wheels. So, and the wheels of a bicycle, that's a super complicated conversation, because the wheels of a bicycle do another thing that gyroscopes do, which is when you push on them in one direction, they move as if you had pushed on them 90 degrees off of that direction. So when you push on a bicycle, it has the net effect of, instead, when you push on a bicycle wheel to yaw it, to turn it left or right, it has the net effect of rolling the bicycle over left or right. So you actually turn a bicycle the way you turn an airplane. You roll it a little bit. And the tires, like with skiing, the tires create a side force against the pavement, and that makes you go around in a circle. So as if you had you were on a string that was tied to a fixed object at some distance, and so you were now going around a circle, like a carousel. So what you do when you turn the handlebars of the bicycle, even though you don't think of it this way because you ride intuitively, is you're pushing the wheel left or right, which, because of the gyroscopic coupling, forces the bicycle to lean left or right. Once you've established the lean angle, you don't continue turning the handlebars. You straighten the handlebars, and the bicycle is going around in a circle. Just like with an airplane, you roll it, and then don't roll it anymore. Just roll it 15 degrees or 30 degrees so that one wing is down relative to the horizon, and then it just goes around and around and around because the wing is producing a lift force to keep you from falling into the ground, and another lift force perpendicular to your velocity vector that causes you to go around in a circle. So anyway, that's the story of bicycling. Stanford, at the time I was there, was famous for making robotic bicycle riders, and the most advanced of those were didn't touch the handlebars. They were no-handed riders. So it's super interesting to see, how you could do that. They were really cute robots because they pedaled the bicycle and, looked a little bit like a person with the sensors above the seat. Okay, so, you have your choice there, spin the body or spin the wheel. It just depends if your sensors can handle spinning the whole body. The nice thing about that is you have no moving parts. You don't have to buy a wheel, no electricity, nothing. Only just the magnetic torque coils. It really doesn't amount to much in the sense of your power budget. A wheel weighs something, costs something, makes grinding noises. It vibrates the satellite ever so slightly, but it does do that. And on satellites like Hubble, they can blur the images, so you have to, isolate them, and all kinds of games go on about that. But anyway, you've got a mechanism, and sooner or later it's going to wear out, and you're going to have to throw the satellite away or send, the space shuttle, the non-existent space shuttle, up to fix it, or some robot or something like that. And probably one of the major lifetime limiters of many, many Earth-observing 3-axis stabilized satellites is when the wheels start to go. And they mostly have the 4-wheel system I was talking about and 2 of them. So, if you have 2... If the rule with NASA is when you get down to, I think it's when you get down to no redundancy or one redundancy, you have to deorbit the satellite while you can still control it. So many times satellites have been thrown away, even though there was still propellant on board, they were still working fine because enough of the wheels had failed. Well, we're better at it now, but it's still, it's a moving part. It wears out with time, despite what the manufacturers say about the fantasticness of the bearings and all that. Okay, let me get to the next slide, which is the one that, has basically taken over the world, 3-axis stabilized. Okay, we've kind of already covered it. You're just going to, my simple-minded Rick Fleeter, Mr. Cartesian coordinates, because I can't handle anything more complicated, cylindrical, polar, spherical. Anyway, in my Cartesian coordinate little world, you put a satellite, because I was, an airplane guy, pilot for a long time. So it was like, okay, put a satellite on the pitch axis, put a satellite on the roll axis, put a satellite on the a wheel, on the Z axis, and because if you think about it, if you put a wheel pointing along the length of the fuselage out the front window and out back toward the rudder, changing that wheel's velocity would cause the airplane to roll, one wing up, one wing down. If you put a wheel vertically so that it was up and down in the cabin, going from your head towards your feet, and then you spun that, you would yaw the airplane left and right. You would move the nose of the airplane left and right. And then, you have the one additional one, which would be pointing along the wingspan, horizontally, perpendicular to the velocity vector. If you spin that one up and down, you'll pitch the airplane up and down on its 3 axes. So to me, it was like, okay, I can do everything I want to do with 3 wheels. And that is exactly true. The problem is if you lose the pitch wheel, the pitch wheel being the one that is aligned with the wingspan, you have no way to control the pitch. You can control the other axes, but you can't control the pitch. And so the game is kind of over at that point. So some people much smarter than me came up with the idea of the tetrahedron. You put a wheel with its axis perpendicular to every face of the tetrahedron. So you have a quadrature of wheels. They're not an orthogonal basis vector, and therefore every one of them has components in common angular momentum vector components in common with the other three. So you can lose any one and you can still span the basis vector, of the three Cartesian coordinates. So the advantage to that is you have a slight amount of redundancy. You can lose one wheel and you've lost a little performance. The other wheels are going to have to work harder, but you basically have the whole thing working. Okay, so 3-axis stabilized satellites, in a way are the simplest, because you pick an attitude some way, and what I'm showing in the little diagram with my little V at the top is that it's pointing at a stars. Let's say it's aligning itself with the star field in some way. It's an astronomical telescope. And then it can slew around by varying the speed of these wheels. When you slow the wheel down, the satellite will move, will roll, rotate in the equal and opposite direction. So by slowing the wheel down, you can cause the satellite to rotate. Then when you speed the wheel back up, it'll stop rotating. Like I said about gravity gradient satellites, if you had a spinning wheel, if you have a wheel on it and you spin it up, the satellite will spin in the opposite direction to maintain zero angular momentum. When you flip 180 degrees, stop the wheel and you'll stop the satellite. So that's how we point a 3-axis stabilized satellite, exactly that way. So, and they sell these little wheels in a box which has all 4 of them in it. So you got to be smarter than me to actually write that control algorithm. But the physical principle of it is pretty straightforward. The next slide, which is 28, is a kind of a maroon color, and that shows our one-wheel sun-pointing satellite. So you can kind of see in the photo on the right and in the block diagram, it looks very much like the other one, except it has a wheel on it. It looks just like the one. If we shut the wheel off, we could spin stabilize it. It would be just like the first one. But this one wanted to stare at targets. And we proposed the one Gigundi wheel because in that period of space history, there were not small wheels, and 4 of them, you would have been out of the category of a small satellite. This was about the smallest wheel you could buy. And it was, kind of 10 inches, a big, heavy hunk of, mechanism. So the interesting thing about that is by spinning that wheel up and down a little bit, we could, what we called head nod, move the satellite up and down in one axis. So the satellite would be pointing at the sun, and then we could point away from, slightly off of the sun axis by up to 30 degrees without losing too much solar panel power, and then, return the wheel to its previous velocity and bring it back, or nod the other way and bring it back. And then the customer and everybody said, yeah, but you don't have wheels on the other 2 axes. That's true. But when you spin a wheel that big, it's very stiff. It doesn't want to turn on the other 2 axes. It's very hard to push, a gyroscope that weighs that much and is spinning that fast. So if you push on it to try to make an error, you're going to get an angular displacement very, very tiny. So it amounts to, in a sense, a poor man's 3-axis stabilization system. In a way, you could build a 3-axis stabilization system exactly this way. Use magnetic torque coils or thrusters to compensate for the disturbance torques that are on the axes perpendicular to the wheel. That would work. What you don't have is an ability to move on those other axes. You don't have any strong actuation. Once you get that wheel spinning, it's going to spin on the axis that it's spinning on. You can head nod it up, rotating around that axis, but it's very hard to move it on the other axes. Well, the customer was happy with that, and we flew it like that. Okay, we're kind of at 40 minutes, so I'm going to quit now. I just want, this is my last picture with a satellite in it. One of my employees actually worked for Dish Network, which then became EchoStar. I really hate these satellite names that have star in them, but that's a whole nother, satellite is about as much of a star as an airplane is a star. It's just, blinking light. It has nothing to do with being, I have trouble with that. A star is a very specific thing. We could call it Echo Moon for that matter. It's just a thing orbiting the Earth that reflects sunlight very rarely. But so many satellites love that star name. It's like, okay, well, the other thing is it can be kind of a negative. SpaceX launches, 40,000 satellites. That's 40,000 new stars, which are going to kind of make it hard to see the other stars that were already there, for a few years before Starlink opened up. So anyway, just to illustrate the geosynchronous satellites are three-axis stabilized satellites. And they're very interesting three-axis stabilized satellites because of how they handle disturbance torques. Because they're in geo, they can't use magnetic torques to, overcome changes when the satellite gets disturbed. And so they have to use propulsion and to make torque, couples. Like I talked about the other day, an engine pointing along the x-axis positive, another engine pointing around the x-axis negative on the other side of the satellite. And then when you pulse those two, you get a pure torque. Kind of like I think of it as a monkey wrench. So, you get a pure torque because you're gripping it on both sides, not just pushing it on one side. And that turns out to be the life limiter for many, many geosynchronous satellites. And so the game is to minimize the disturbance torques, which are pretty interesting and pretty much explain how the satellite is designed. Since I'm on that subject, let me finish it and then I'll quit. If you look at the two big antennas, which are used, the satellite is, 39,000 kilometers away from the equator and a few more thousand away from where most of the clients probably are in North America, Australia, Europe, wherever. It has to have big antennas to concentrate the signal because, the Earth from that altitude is relatively small. And you'd be a big waste of your power to just radiate into space with an isotropic antenna. So that a big part of the engineering of these satellites are those antennas. The trouble with a big dish like that is a lot of solar photons hit it. If you only had one of them, it would be constantly torquing the satellite to, spin in that direction. It would be kind of a wind vane. So you need two, and you need them to be equal and opposite. So the satellites are in geosynchronous orbit over the equator, and they are oriented so that one of those antennas is on the north side, and one of those antennas, they call it that. That's the north antenna and the south antenna. That's how you know which one you're working on. I'm working on the north antenna. So that kind of gives you a coordinate system for the satellite. The other big surface area that these satellites have are the solar panels, which you can see, on the front to the right, folded up the way I talked about how they do a click-clack thing with one pushed against the other, and the same deal. Those are east and west. So they call them the east solar panel and the west solar panel. So that gives you kind of, a balance of those solar pressure torques, which is the predominant disturbance torque at that altitude. There is a certain amount of gravity gradient. And in fact, in the 60s, it was attempted to do gravity gradient stabilization from GEO with Gigundi booms. And it worked, but it was considered not worth it because the quality of pointing you get is very low. And then you have to augment it with wheels. And of course, people say, well, if you got wheels, the hell with it. We'll just use the wheels, right? So these satellites have wheels, that spin on the 3-axis or on the 4-axes, in two sets of them and so on. And actually, they mostly go the 17-year lifetime with, between the original and the backup and so on without a problem. They also have to have batteries that can be charged and discharged. An unfortunate fact of GEO is 20 minutes a day you're in eclipse. Yikes. For those 20 minutes, you got to deal with the whole battery thing. But at least it's only 20 minutes, so you don't have to run the satellite very long on batteries. So 20 minutes for a satellite that's consuming, 10,000 watts or something like that is, a significant, what do they call it in the Tesla world? Power wall, I think. You need a fairly significant power wall to take your 10,000 watt satellite through a 20-minute power outage. And then the other prominent thing that you see on the satellite, looking at that one, is an aluminum cylinder, or it looks like an aluminum cylinder. It's actually some other kind of cylinder. That's a rocket propellant tank. And there's two of those. And the one is symmetrically, one's on the north side, one's on the south side. And what they're trying to do is minimize, balance the mass moment of inertia so that the gravity gradient torques are going to be approximately zero, because from a mass moment of inertia point of view, it looks like a basketball. That's what you're hoping to accomplish. So the satellite is tall, which gives you a big moment of inertia tensor, but then you go and deploy the antennas, and then you go and deploy the solar panels, and you're tall on all three axes. So if you look at the moments of inertia on the three axes, they purposely design it so that they come out approximately equal, so that there's no gravity gradient torque. So you balance the gravity gradient torque. There's no aerodynamics up there. Balance the solar photon pressure, And the thing uses very, very little. I mean, I've been in the operator's room watching. What they monitor is the wheel speed. Every time the satellite develops an error, the wheels will automatically speed up or slow down. And that is one of the most boring things you can ever do. The whole day passes and the numbers don't seem to change, or it changes a little and then changes back. So they do a great job of balancing it. So they minimize the propellant necessary. There's a million interesting engineering tricks that go into making these geosynchronous satellites work and work for a long period of time. And we're going to see a film in the class called Building a Satellite, which was done by the BBC. Probably the best engineering film ever done on satellite building. And I say that without reservation. So it talks about many and many of those things. So given that it's 45 minutes, I'm going to let you go, even though I'd love to go on and on forever about geosynchronous satellites. And I've worked on a few of them back, mostly in the 80s and 90s. And it's a super interesting field. And it was going small. The Israelis built the first small geosynchronous satellite. And now there's a large variation in the sizes, from the very biggest ones that we can launch on Ariane 5 and Falcons and stuff like that, down to much smaller ones that actually ride to geosynchronous. We don't see little ones yet, like CubeSats, but the day will come. Part of the reason we don't see them is the Air Force can't track them, and so they don't like you launching things that that they can't see. So up at GEO, you've got to be a little bigger. The point of the little photo of the family watching, I think they're watching the Apollo landing on the moon, actually, is that, we take long distance television for granted, but geosynchronous satellites, starting with, the SATCOM, starting with the SYNCOM, the one, the super old, the first geosynchronous satellite, they were all basically used for the same thing, even up to today, which is, the big customer relaying television all over the place. Okay, I hope this was somewhat enlightening, and I will be back the last time. There'll be the fourth podcast in this series to talk about, some of the various ways you choose between. There isn't really very much to do, but I just don't want to do it, on the fly. I want to summarize the environmental torques and summarize the trade-off between the different possibilities that you have. So I'll do that in an organized way. Should be a short podcast. Okay, thanks for your attention. Talk to you soon. Bye.